Hello, everybody. Welcome back to Markov processes. In the last video, we talked about first step analysis for Markov chains. And I think this is one of the most powerful and fun things for discrete time, discrete state space Markov chains, because it allows you to answer some pretty complicated questions about probabilities and expectations and first hitting times by exploiting that Markov property by saying, I'm going to take one step and then I'm going to reevaluate what's going on. So if the last video made sense to you, then I would skip ahead in this video because I'm going to do a little more of that just to make sure we have it down. But again, nothing really new until we hit mean pattern times. And if you look in the description box below, you'll see a link for mean pattern times, and you might want to jump to that point in the video. I'm going to share my screen. Let's get going. In this video, I'm going to focus on computation, so I'm not going to make up a word problem. I'm just going to have a state space and a totally made up transition matrix, and we'll answer a few questions. So my state space here is going to be the integers 1, 2, 3, 4. And the transition matrix, I'm going to have a 1, 2, 3, 4. And across the top row, I have probabilities 0.1, 0.8, 0, and 0.1. Across the second row, I have probabilities 0.4, 0.1, 0.2, and 0.3. Across the third row, I have 0.2, 0, 0.6, and 0.2. And across the fourth row, I have 0.3, 0.5, 0.1, 0.1. And while I'm here, let me go ahead and label these columns. So I have a bunch of questions for you similar to last time. They're really the same categories of questions. Let's see if we understand it a little better now. So question 1, I'm going to start at some state, say state 3. And I want to know the expected number of steps it's going to take to hit state 1. So to answer this question, I am going to set up a hitting time. A hitting time as opposed to a return time. A hitting time is the very first time the chain hits a certain value. And this could even be at time 0. So I am going to let t be the minimum over all n greater than or equal to 0, such that the chain at time n is in state 1. And what we want to compute is the expected value of t given x0 is 3. Now, as you'll recall, the first step analysis says, let's take one step and reevaluate, and potentially we're going to be somewhere else, and we're going to want to still continue to find the expected number of remaining steps to hit state 1. And that means we're going to want to keep restarting where the chain is. So I'm going to let u sub I be the expected value of t given x0 is I. And now what we want is u sub 3. And we know, for example, let me draw a picture here. This is my state space. 1, 2, 3, 4. If I start a chain at state 1, and I want to go until the first time I hit state 1, I have already hit state 1. It's all over. I don't go anywhere. The number of steps it takes is 0. So we know in this notation here that U1, the expected number of steps to first hit state 1 when you start in state 1, is 0. What is not 0 is U3. That's going to be the more interesting thing that we're going to find right now. So let's write an equation, U3. Again, I'm going to try to draw a picture down here, states 1, 2, 3, and 4. And we're going to imagine starting at time 0 at 3. And we want to go until we first hit state 1. So I have to move. I'm not at state 1. So U3 is going to start off with a 1 step plus. And now we're going to see what happens. And we're starting from state 3. So from 3, if you look at the 3 row of the matrix, you see we can go to states 1, 3, or 4. In this case, we can't go to 2. So a sample path forward to time 1 is either going to go to 1, stay at 3, or go to 4, with probabilities 0.2, 0.6, and 0.2 respectively. And so let me write that down. With probability 0.2, we go to state 1. And that means it's over. we have hit state one. So I'm going to count 0 time steps. I have my 1 time step and 0 more. And then with probability 0.6, I'm going to start at 3 over here, and I'm going to stay flat at 3. And that means that I have to count that 1 time step that we took and now start all over as if this is time 0. So we're really going to take advantage of that Markov property. Once we know where we are, that's all we need to figure out where we're going to go, and we can relabel time. So with probability 0.6, I move from 3 to 3, and now I start over from 3. So I get a U3 here. And finally, with probability 0.2, I go from 3 to 4, and now I want to start there. Let me move this over a little bit. And that's all there is to it. Okay, so we have an expression for U3 and it involves U4. So let's write an expression for U4. U4, this means we're starting the chain at state 4 and we want to go forward until we hit state 1, and that's our stopping rule. So we're going to have to take at least one step because we're not at state 1 right now. You can see that I can move from state 4 to 1 or 2 or 3 or 4. Now, if we move to 1, it's over. And the picture would look like this, going down to state 1. And we've hit state 1 and there's 0 more steps, but we do have to take at least one step. So I'm going to start with a 1 plus, and then this probability 0.3 times 0, meaning it's over, take 0 more steps. And then with probability 0.5, I want to start again at state 2. So I'll put a U2 in there, which is the expected time starting at state 2. So again, we're kind of relabeling time 1 and calling this time 0 and saying we are at state 2. Now where do we go? So continuing across the matrix here with probability 0.1, I move from 4 to 3, and I have to start counting from there. And with probability 0.1, I move from 4 to 4, and I need to start counting from there. So this equation involves an unknown U2, so we're going to need to write another equation, an expression for U2. This means that we are starting the chain at state 2, and I'm going to look at the 2 row of the matrix. Oops. And you can see that, well, we have to take at least one step starting here at state 2 to hit state 1. So let me put a 1 plus in here. And now looking at the 2 row of the matrix with probability 0.4, I go from state 2 to state 1, and that means it's over, 0 more steps. With probability 0.1, I go from state 2 and stay flat at state 2, and then we're going to call that time 0 and start over. So with probability 0.1, I'm going to now count the expected number of steps to first hit state 1, starting from state 2. With probability 0.2, I move from 2 at time 0 to 3 at time 1. And so I'm going to put a 0.2 here, and then time 1, I'm going to reset that and call that time 0. And now I want to consider I'm starting at 3. How many more steps does it take? Because we already have the first step over here. So starting at state 3, how many more steps does it take to first hit state 0? And we're calling that U3. And then finally, starting from state 2 with probability 0.3, we're going to go to state 4, and we have to count from there. So we have a system of equations. So I went ahead and solved these offline. You could back substitute. You could move everything like to the left side, except for maybe these constant ones, and write it as a matrix vector and take an inverse. However you want to get there, that's kind of not what I want to focus on today. It's coming up with these equations. So I solved this offline, and I got that U2 is approximately 3.14. U3 was approximately 4.16, and that's what we wanted to compute in this particular problem. But since we get it for free, U4, let's write it down, is approximately 3.32. Okay, so that's the first type of question in the ones I want to cover for first step analysis. So you start somewhere and you have a stopping rule and you want to know the expected number of time steps to get to that stopping rule. This is what I'm calling a U problem in this course. I mean, if you go out into the world and talk to other people about you problems. No one's going to know what you're talking about. So it's just for this course. Okay, let's go to another question. I'm going to call this question 2 or Q2. It's going to be another type of first step analysis question. I'm going to start in state 3 again. And I'm going to go until we hit either state 1 or state 4. So the stopping rule is if you hit state 1 or state 4, stop. When this chain stops, it's going to be in state 1 or state 4. And I want to know the probability that when it stops, it's actually in state 4 versus state 1. So let me write that down. For the purpose of this class only, this is what I call a P problem. We've got some problems with U's and P's and W's, and this is a probability that we want to compute. So I'm going to use the letter P. And let's set up some notation. I'm going to let T be the first time, and this will allow even time 0. So if you start a chain in state 1 or state 4, you don't move at all. You have stopped immediately. But this is going to be the first time that the chain is either in state 1 or it's in state 4. And I want the probability that the chain X at time t is 4. And I want this given that at time 0, we were in state 3. So a first step analysis is going to have us changing this number up. Let's get some notation. I'm going to let P sub I be the probability that when we stop, we're in state 4, given that we started in state I. And so we want P3. And we know a couple of other P's right off the bat. Here are our states, 1, 2, 3, 4. Suppose we start in state 1, and we're going to go until we hit state 1 or state 4. In this picture, we're not going anywhere. We have our stopping rule met at time 0. We are not going forward. So what is the probability for this scenario that we ended in state 4 versus state 1? That's 0. We're not getting to state 4. So we know that the probability starting from 1 that we end in state 4 is 0. Similarly, if we start at time 0 in state 4, the stopping criterion has also been met. And this time we ended in the place we're more interested in. You know, we stop when we hit 1 or 4, and we want to know the probability that when we stop, we're at state 4. So this chain stops immediately in state 4. And that means we know the probability that when we start from 4 and we follow this stopping rule, that when we stop, we're in state 4 is 1. That's definitely where we're stopping. So let's come up with an equation for P3. Now here, I'm not counting time steps. I'm not counting steps on anything. I'm not counting hits. It's just a probability question. We talked last time about how to formalize what we're doing in the U case. And I have a homework problem for you where you get to formalize what we're doing in the P case. So this is really just about being computational and just getting some problems done, but there's no 1 plus. We're not counting anything. But we are starting at state 3. Let me go get rid of this point in our graph. We're starting right here. And if I go back up to the 3 row of the matrix, you'll see that I can either go to state 1, in which case it's over. I can go to state 3, in which case it's not over and we have to look from there, or I can go to state 4, in which case it's over. And so the first probability right here, 0.2, I'm going to have probability 0.2 times. So when that happens, that means that the path went from 3 to 1 in 1 time step. What is the probability that we end in state 4? We have ended because we're in 1 or 4, but the probability that we end in 4 is 0. Didn't happen. With probability 0.6, I go from 3 to 3. We stay flat. And now I want to compute the probability starting from 3. I still am aiming to hit 1 or 4, and I want to know the probability I hit 4 before I hit 1. And finally, with probability 0.2, we go from 3 to 4. And so I'm going to get a 0.2 here, And then the probability that we end in state 4 is 1, because this points 2 represents a move from 3 to 4. So I could have written, P1 here and P4 here, because they're already defined to be 0 and 1. And this is an equation that only involves one variable. So let's solve for P3. I'm going to move all my P3 stuff to the left. And I get P3 is 0.2 over 0.4, or 1/2. And this means that if we start in state 3 and go until we hit state 1 or state 4, we computed that the probability we end in 4 is 1/2. So the probability we end in 1 is the rest of that probability, 1 minus 1/2, which also happens to be 1/2 here. From a simulation point of view, you could imagine, actually, let me get a bigger graph here. You can imagine starting at state 3, maybe going to 2, staying flat, going up to 3, staying flat, going down, hitting 1. And that is your stopping criterion. And that happened, well, I don't care how many steps, but 1, 2, 3, 4, 5 time steps. And if you started in 3 all over again, maybe you stay flat and then you go to 2, and then maybe you jump up to 4, in which case it's over. So sometimes these paths end in 1 and sometimes they end in 4. And if you were to repeat this over and over and over again, many, many times, if you were to simulate this, then half the time you're going to end a path in state 1 versus state 4. So I have a third question for you in first step analysis. I'm going to call this Q3. And this is what I call a W problem. So what's happening here is we're going to start at some state. I'm going to start, let's mix this up a little, in state 1. And I'm going to go until we hit state 4. So that's the stopping rule. And I want to compute the expected number of hits on state 3 along the way. This is, for the purpose of this course, only what I call a W problem. So U problems are you start somewhere and you want the expected number of steps to hit something. P problems are you start somewhere and you have a stopping rule that consists of stopping when you hit 2 or more states, and you want the probability that you stop in a particular state. The W problems, as I call them, we're going to start in a state, we're going to go until a stopping rule is achieved, and along the way we want to count an expected number of hits on a state, could even be a whole set of states. So I am going to let Wij be the expected number of hits on state J, starting from state I and ending at state K. And what we want to find W1, 3, 4. So we're going to start here. We're going to go until we hit this. And in between, we want to count the expected number of hits on state 3. Let's go for our first step analysis. I'm counting hits, but not every time step. It's not a U problem where you count every time step until something happens. So it may be possible, it is in this case, it is possible to go, say, directly from 1 to 4, or maybe from 1 to 2 and 2 to 4, or maybe spin around in some states. It's possible to hit that stopping rule that we hit 4 without ever hitting 3. And that's why there is no 1 plus here. So no 1 plus, because I'm not counting every time step, only the time steps where I hit 3. But I am starting at 1. I'm going to look at the 1 row of the matrix. And with probability 0.1, I go from 1 to 1. So I get a 0.1. And now I'm starting at state 1. And I want to count the number of hits on state 3 with the stopping rule of stopping at state 4. And with probability 0.8, I have moved from state 1 to state 2. So now I'm starting at state 2, and I want to count the hits on 3 before stopping in state 4. And finally, with probability 0.1, we go from state 1 directly to state 4, and we don't hit state 3. So we're going to count 0 hits on state 3. This is what I would call game over. Okay, so for this equation, you'll see that we have this W234. So let's find an equation for that. Starting in state 2 and going until the first time we hit state 4, what is the expected number of hits on state 3? I may not hit it at all. So, and I wouldn't worry about like looking at the matrix and saying, oh, I can't go directly from 2 to 4, or the saying I may not hit it at all is just a general saying. The specific Markov chain might force you to do one thing over another, but you should just let the probability work that out for you. So what I mean by that is don't go in and say, oh, I definitely can't go to 4, so let me not consider certain cases. So starting from state 2 with probability 0.4, I go to state 1. And so let me put a 0.4 here. And now starting from state 1, I want the number of hits on 3 where my stopping rule is state 4. From state 2, I go to state 2, I stay flat with probability 0.1. So now starting at 2, I want the number of hits on 3 before I stop at state 4. With probability 0.2, I go from state 2 to state 3. So now starting at 3, I want to count the number of hits on 3 before going to 4. And we have hit 3, but we don't have to deal with that yet. Wait for the next line. And I do have one more term to put in here. So with probability 0.3, we go from 2 to 4. And it's over. That's our stopping criterion. We're counting 0 hits on state 3. So it looks like I have at least one more equation to write down here. There's another unknown that has come up. That's not it. It's this one, W334. So let's try to write that one down. And I am just going to grab the, oops. Oh, I was going to grab the 3 row of the matrix, but I think I can fit it in here. So the 3 row of the matrix is up here. We are starting at state 3. The picture is, if you imagine simulating this Markov chain, 1, 2, 3, 4, we're starting at state 3, and we're going to go until the first time we hit state 4, and we want to count the expected number of hits along the way on state 3. Now, because we started at state 3, we already have 1 hit to count. So this equation does have a 1 plus. And you will get that from these Wi, j, k equations whenever j and I are equal. But yeah, let me back up and so we can see the matrix. Looking at the 3 row, with probability 0.2, I go from state 3 to state 1. And now starting at state 1, I want to count the number of hits on 3, ending at state 4. With probability 0.6, I go from state 3 to state 3. The sample path stays flat. And so starting from 3, I want to count the number of hits on 3 before hitting 4. And finally, starting at state 3, with probability 0.2, we hit state 4, and that is the stopping rule. So I get a 0.2, and how many hits am I going to get on 3? I'm going to count 0 at least for that step because I ended. We're at 4. There's no more hits on 3 to accumulate. And I think we have enough equations. 1, 2, yeah, it looks like we have 3 unknowns and 3 equations. So I'm going to go solve that. Okay, I got W134 to be approximately 0.9756. I got W234 to be approximately 1.0976. And I got W334 to be approximately 2.9878. So we wanted W134. And so that's our first little guy over here. By the way, the order of these that they're getting larger maybe makes sense, or at least this one, W334. You're starting at 3, you're already counting a hit on 3. So I would generally expect this to be higher than the others, although I can't say for sure because we could have some extreme matrix where if you start at 3, you move away in 1 step and you can not come back to 3, or you move to something where it's highly unlikely that you come back to 3. But yeah, for the most part, if you're starting at 3 and counting hits on 3, since you have that head start, You probably expect that number to be larger than the other two. Okay, so those are the three basic first step analysis questions, but I want to take question 1 and question 3 and add a little bit of a complication. So this is a strange ordering, but I'm going to call this question 1B. Remember, in question 1, we started at state 3, and we counted the expected number of steps until we hit state 1. Now I want to count the expected number of steps until we first return to state 3. In this case, we are no longer going to have the stop the chain immediately at time 0. We're going to start at state 3, and we're going to allow ourselves to move away. So I am going to let t be the return time to state 3. And writing this alone, the definition of t does not make it a return time unless I am conditioned on starting at 3. But I'm going to let this be the minimum over n greater than or equal to 1. Now before, in question 1, this was all n greater than or equal to 0. But I want to force myself to take at least one time step. And if we hit time 3, and if we hit state 3 at times greater than or equal to 1, we have returned to 3. And I want to find the expected value of t given x0 is 3. So one more time, we're starting at 3 and we want the expected number of steps to return to 3. We want to not just count the first time we ever hit 3, which happens at time 0, but return. And that could happen in one step or any number of steps. So we're going to keep restarting. We're going to do a first step analysis. So I need to define, I'm going to use the same letter. You know, this might be, I don't know if this is worth the confusion, but it's the same type of problem. So I'm going to keep the U problems, the P problems, and W problems. I'm going to let UI be the expected time to stop at a time greater than or equal to 1, given x0 is I. And we want U3. Notice U3 is no longer 0. Well, it wasn't in question 1 either because our stopping rule was 1. But if I were starting at state 3 and I wanted the expected number of steps to first hit state 3, and so if I define t to be the minimum of all n greater than or equal to 0, then I have hit state 3 right away if I start at 3. And in that case, U3 would be 0. But we are getting to move here. So I am going to grab the matrix and I'm going to consider the third row, U3. We're starting at state 3 and I want the expected number of steps until we return to 3. So I do have to take at least one step. And now I'm going to look at the 3 row of the matrix. With probability 0.2, we move from 3 to 1. And now I want the expected number of steps until I return to 3, starting from 1, and that is called U1. With probability 0.6, I go from 3 to 3, and it is over. We have returned to 3, and we count 0 more steps. And finally, with probability 0.2, I have gone from 3 to 4. And so I haven't reached that stopping criterion of returning to 3. So now I'm going to start from state 4, counting the expected number of steps to first hit state 3. I no longer really have to think about it as a return because we have already left state 3 and we moved to state 4 and we're resetting that to be time 0. So let me get this picture here. 1, 2, 3, 4. Starting at 3, in this last scenario, I moved to 4, and now I'm calling time 1. I'm resetting that to be time 0, and I don't care about returning to 3 anymore. I just care now about the first time I hit 3. It's now a first hitting time. So there's our equation for U3, but it does depend on an unknown U1 and U4. So let's go for U1. Starting from state 1, I am going to go until I hit state 3, and I have to take one step. So this is a return time again, but what we're thinking about here is we already started at 3 and we've taken one step to state 1, and now I'm calling this time 0. And all I care about now is the first time I hit 3. I don't need to think of it in terms of return anymore, just the first hitting time going forward on state 3. So looking at the 3 row of the matrix with probability 0.2, I go from 1 to 1, and I start over counting the expected number of steps it takes me to hit state 3, starting from state 1. Oops, sorry, I'm looking at the wrong row. Okay, so looking at the 1 row of the matrix with probability 0.1, I'm going to go from 1 to 1, and I'm going to start all over counting from state 1. With probability 0.8, I'm going to go from state 3 to state 2. And now I want to go forward and count the expected number of steps to hit state 3, starting from state 2, and we call that U2. And with probability 0.1, I go from state 1 to state 4. And I want to count the number of steps starting from there. I have 2 equations now, but I still have 3 unknowns. We're going to need an equation for U4. So starting at 4, I want to go until I hit 3. That's going to take at least 1 step. Looking at the 4 row of the matrix with probability 0.3, I move from 4 to 1, and now I want to start counting the expected number of steps to hit state 3, starting from state 1. So that's U1. With probability 0.5, I go from 4 to 2, and I want to multiply by U2 because I want to start counting from 2. With probability 0.1, I go from 4 to 3. So how many steps am I counting to hit state 3? I'm counting 0 more steps. There's my first step counted to take me from 4 to 3, but I hit 3 and it is game over again. And with this probability 0.1, I go from 4 to 4 and count the expected number of steps starting from state 4 to hit state 3. So there's your system of 3 equations and 3 unknowns. And I went ahead and solved this, and I got U1 equals 3.75. U3, which is the thing we wanted to solve for, came out to be 2.50, and U4 is 3.75. So we had question 1, which was a U problem. That means you start in some state and you go until you hit some state and you want the expected number of time steps. Then we had question 2, which was a P problem. And that means you start at some state and you go until you hit one of a couple of states or one in an entire set of states. And you want to know the probability that you ended at this state versus another state. Or another state, or another state. And then we had the third problem, which I call the W problem. And that's where we start at some state and we go until we hit some other state and we count the expected number of hits on some intermediate state along the way. Then we changed the U problem and we called it question 1B. And what we changed was we had a chain that started at a state and we looked at the first return to that state. So we had to allow ourselves to step away. And now I want to do the same thing with the Q3, the W problem. So I'll call this Q3B. So I'm going to start at 1, and we're going to go until we return to 1. And along the way, I want to count the expected number of hits on state 3. So I'm going to use the same notation. I'm going to let Wij be the expected number of hits on J, starting from state I and ending at state K. And I want to find in this notation W131. So when we did this problem, the other W problem, I didn't say that kind of thing that I've said with the other ones. Oh, we know this one already and know that one already. But if this were the older W problem, we would be starting at 1, counting the hits on 3 before our first hit on state 1. And that would be 0 because we would stop the process immediately. Starting at 1, and we have hit 1. But here we are allowing us to move away, potentially move away from state 1. So this is not going to be 0. This is actually the thing we want to solve for. Let's start at state 1. So let's look at this 1 row With probability, remember, I don't put a 1 plus here because I'm not counting every time step. I'm only counting the time steps when we hit state 3. So with probability 0.1, we go from 1 to 1 and it's over. We have returned to 1 and we count 0 hits on state 3. Whereas with probability 0.8, we move from 1 to 2. And now, starting at state 2, I want to count the number of hits on state 3 before I hit state 1. And with probability 0.1, I move from 1 to 4, and we're going to start counting from there. So let me move this over. I need a little more space. Okay, so I get a 0.1 W431. Starting at 4, count the expected number of hits on 3, when the stopping rule is to stop at 1. So there's a couple of unknowns here. Let's go for W231. I'm going to look at the 2 row of the matrix. I am counting the expected number of hits on state 3, and starting at 2 and ending at 1, I don't know if I'm ever going to hit 3, so there's no 1 plus. But with probability 0.4, we have gone from 2 to 1, and it is over because hitting 1 at a time greater than or equal to 1, not at time 0, is the stopping criterion. With probability 0.2, with probability 0.1, I go from 2 to 2, and now starting at 2, I want to count the hits on 3 before stopping at 1. With probability 0.2 over here, I'm at 3. So starting at 3, I want to count the number of hits on 3 before stopping at 1. And with probability 0.3, I go to state 4. So starting at 4, I want to count the expected number of hits on 3 before returning to state 1. Okay, what else do we not know? We do not know W431. Starting at state 4, going until we hit 1, what's the expected number of hits on state 3? With probability 0.3, I go from 4 to 1, it's over, I count 0 hits on 3. With probability 0.5, I go from 4 to 2, and now starting at 2, I want to count the hits on 3 before stopping at 1. With probability 0.1, I go from 4 to 3, so now starting at 3, I want to count the number of hits on 3, stopping at 1. And with another probability 0.1, I go from 4 to 4, so now starting at 4, I want to count the hits on 3, stopping at 1. And it looks like we also need an expression. There's another unknown in here, W331. W331 says we're starting at state 3. We're going to go until we hit state 1, and then it's over. And I want to count the expected number of hits on state 3. So in this case, we already have 1 hit on state 3. So just like it was in the previous Wij, problem, if I and j are the same, then that's the equation that you're going to get a 1 plus in. Now looking at the 3 row of the matrix with probability 0.2, I go from 3 to state 1, it's over, 0 more steps. With probability 0.6, I go from 3 to 3, so now I want to start counting from there. And with probability 0.2, I go from 3 to 4, so now starting at 4, I want to count the hits on 3 before stopping at 1. We have a system of equations, and we want to solve for W131. I'm too lazy to solve this one, but that's how you do the problem. So to finish off today's lecture, I want to talk a little bit about mean pattern times. We're going to perform an experiment like flipping a coin, and we're going to flip it not until we get heads or tails, but until we see a whole pattern of a particular pattern consisting of various heads and tails. So let's flip. I'm going to make it a fair coin. It doesn't need to be a fair coin. I'll show you where in the problem that's going to change if it's not a fair coin, but we're going to go until we see the pattern tails, heads, heads, heads. One way we can do this is we could do this by first step analysis. We could make a chain on the state space consisting of, so like this is just one idea. This is not going to be what we're going to do, but we could make a chain on the state space consisting of heads, 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 tails, all the way down to tails, 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 tails. So that's going to be 2 to the 4th or 16 different possibilities. And if you remember when we talked about a longer history in a Markov chain, I can't remember, I think it was good and defective widgets or something. We are going to be talking about states overlapping. So if you are at heads, 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 then the next thing could be heads, or if you're at heads, 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 the next thing could be tails. So you're going from these 4 to these 4, or down here from these 4 to these 4. So this matrix, if you made a 16 by 16 matrix here, is going to have a lot of zeros in it. Let me just write out the first row. Heads, 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 heads. And then up here, heads, 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 tails, all the way to tails, 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 tails. The first row of this matrix is going to have probability 1/2. That's the probability of getting that final heads, which takes you from 4 heads to, I was going to say 4 different heads, but you've got overlap. And we can also go to from heads, 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 heads to heads, 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 tails. And the other probabilities are 0. And I'm not going to finish out this matrix, but you can consider a Markov chain running on this large state space. And have I used any letters? I haven't used any letters yet. So you can let like xn be a Markov chain on the state space. I should have labeled it, but I haven't. So I'm just going to write this once more. So it's going to walk around this 16-point state space with transition probabilities given by this matrix. And we want the first hitting time on this pattern. And in this scenario, or in the way I set this up, we could start at that state and the hitting time will be 0. But what did we originally really want to answer? We wanted to answer the number of flips. So we could find the first hitting time on the state tails, heads, heads, heads for this Markov chain xn. And actually, we want to find the expected first hitting time. That's going to be a U problem. And then the final answer is going to be that answer plus 4. Because if the expected hitting time is 0, in terms of flipping the coin, that means you started off with tails, heads, heads, heads. So the final answer is going to be the expected hitting time for this chain on that state plus 4. This is a U problem, except we don't have a starting state. So you need to consider all possible starting states. And if you flip a fair coin 4 times, you are equally likely to see heads, 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 tails, heads, heads, tails, heads, all the way down to tails, 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 tails. So they each get probability 1/16. So the expected, let's see, if we let t be the minimum over n greater than or equal to 0, such that xn is heads, tails, 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 then we want the expected value of t, period. We weren't given a starting value, but we can do what we did before by conditioning on where we're starting. So we can write this as the sum. This is going to look a little weird. I'm going to say I goes from 1 to 16. So here I represents one of those 16 patterns of heads and tails. And I'm going to look at the expected value of t, given that x0 is I, times the probability that x0 is I. Again, I is 4 flips. And this is going to be 1/16 all the way across. So I'll get a 1/16. the sum as I goes from 1 to 16 of the expected value of t given x0 is I. So this would be what you would call UI, and you would solve the system of equations. And usually we solve a big system of equations and we get a U1 through, in this case, U16, and we only care about one of them. But here we care about all of them. We have to go and put them back in this sum. And then when we're done, this is the expected hitting time. We're going to need to add 4 to the final answer. We could do that. And I'm just being lazy because I have a better way to do it, but I usually like to do it the bad way first so that you can really appreciate the better way when you see how long it took. But yeah, I feel lazy, so let's go to a kind of slick way to do this problem. Again, we're still searching for the pattern tails, heads, heads, heads with our fair coin. And I'm going to start flipping, and I want to know the expected number of flips until I see that pattern. So let's let S be the number of flips until you finish out that pattern. You see it and you finish it. Note of caution, the method we're about to do is only going to work for a non-overlapping pattern. So a problem pattern could be something like tails, heads, heads, tails. And the reason, well, here's what I mean by overlapping. So if I go on and write heads, heads, tails, you can see the pattern tails, heads, heads, tails right here. And then you can see the pattern again, but they're going to be sharing that T. And I'm not sure if that makes sense. What I mean by overlapping, because you might think there's several H's here. Is this not overlapping? Hopefully this makes sense. But if not, wait till we get to the point of the problem where we need this non-overlapping property. If we do have an overlapping pattern, it doesn't mean we can't do this problem in a slicker way than that first step analysis. We're going to have to use something known as a martingale, which is another kind of stochastic process that I do hope to get to at the end of this course, time permitting. So we need a non-overlapping pattern, which we have here. And so I'm going to let S be the number of flips until we see it. Now, note that S takes on values 4, 5, 6, 7 on up. Oh, I guess that S looks like a state space now. I can't win with these letters. It is not a state space. It is the number of flips until we see the pattern. So S is taking values in there. And so we could find an expression for the probability that S equals N. And this would be for N equals 4, 5, 6 on up, or you can have it for all N, but you can define this probability to be 0 in some places. And then we can find the expected number of flips by taking the sum as N goes from 4 to infinity of N times the probability that S equals N. But it's going to be more convenient to instead consider finding the probability that S equals N plus 4 for N equals 0, 1, 2 on up. A little unmotivated right now, but wait till you see it. Okay, so to write an expression for the probability that S equals N plus 4, I am going to condition on the value of the process at time N plus 1, N plus 2, N plus 3, and N plus 4. And the process can take on, in each of those time steps, one of two values, heads or tails. So I'm going to sum over I, J, K, and L. Each one of these sums actually takes two values. So I could be heads or tails. Yes, right. This should be a number. So you could map heads to 1 and tails to 0 or something like that. But I am going to look at the probability that S equals N plus 4, given X N plus 1 is I, X N plus 2 is J, X N plus 3 is K, and X N plus 4 is L, times the probability that X N plus 1 is J, X N plus, sorry, that's I, X N plus 2 is J, X N plus 3 is K, and xn plus 4 is L. This second probability, super easy for us.
Super easy, barely an inconvenience. Oh.
It's just a coin. It's a fair coin, and the flips are independent. So this is 1/2 times 1/2 times 1/2 times 1/2, which is 1/16. And if you did not have a fair coin, so if you had a coin that came up heads with some probability P and tails with the rest of the probability, then here you would have some kind of multiplication of P's and 1 minus P's. But we have now the probability that S equals N plus 4 is equal to 1/16 times this sum over I, J, K, and L of the probability that S equals N plus 4, given xn plus 1 is I, xn plus 2 is J, xn plus 3 is K, and xn plus 4 is L. So the event on the left side of the conditional line, this is the event that the first time we see the pattern being tails, heads, 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 is at time n plus 4. So we're going along. These are like positions for coin flips. And the first time we see the pattern tails, heads, heads, heads is at time n plus 4. The probability that we see this pattern, tails, heads, 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 in time steps n plus 1 through n plus 4 is going to be 0 if the values we're given that are in those time steps and observed are not tails, heads, heads, heads. So what I'm trying to say is, although there are several things in the sum, this probability is going to be 0 because it's saying that the pattern occurs at time n plus 4. And that means that I, J, K, and L must be tails, heads, heads, and heads, or that probability, this probability here, is going to be 0. So from this four-way sum, almost everything is 0, but we get the probability that S equals n plus 4, keeping the only non-zero term. I've got this 1/16 out front. The probability S equals n plus 4, given xn plus 1 is I, xn plus 2 is J, xn plus 3 is K, and xn plus 4 is L. One term left. We're really narrowing this down. Let's take a second to note a couple of things. Note that, number 1, or my first bullet point, if S is equal to n plus 4, then that implies that S is greater than n. I'm so clever. And if S is greater than n, that does not imply that S is equal to n plus 4. S could be n plus 1 or n plus 17. However, in the universe where this stuff is true, where the flips at time n plus 1 through n plus 4 equals tails, heads, 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 I claim that this implication actually holds. Let's try to draw the picture. So I've got some kind of places where I've got flips, like little slots to put them in. And if S is greater than n, then that means there is no tails, heads, heads, heads pattern that has appeared in here. And then I have 3 more positions at time n plus 1, n plus 2, n plus 3, and n plus 4. So if the pattern hasn't appeared yet by time n, but we're in the conditional universe where at time n plus 1, we have tails, and at time n plus 2, n plus 3, and n plus 4, we have heads, then this is the time n plus 4 is where the pattern first appears, given that it did not appear back here. And here is where an overlap could be an issue, because if I try to draw this again with an overlapping pattern, so let me put this in the yellow color we were using, the tails, heads, heads, tails. If in the last 3 of the first n, I have tails, heads, heads, and I'm in the conditional universe where at time n plus 1, n plus 2, n plus 3, and n plus 4, I see the pattern. This does not mean, so again, I have that I did not see the pattern here, but the pattern occurs at time n plus 1. So if I have an overlapping pattern, then just because I haven't seen the pattern by time n and conditional on the pattern being sitting here at these time points, if I had an overlapping pattern, that doesn't guarantee that the pattern is first observed out here. Because of the overlap, it might take only one of these or maybe two of them to finish off the pattern. We don't have this problem with an overlapping, with a non-overlapping pattern. So again, if we did not see the pattern by time n, and we conditioned on seeing tails, heads, heads, heads at time n plus 1, n plus 2, n plus 3, n plus 4, and we have a non-overlapping pattern where, say, this is not finishing a pattern that started further back, I can say that if s is greater than n, then in this conditional universe, I must have s equals n plus 4. So let me summarize that by saying s is greater than n if and only if s equals n plus 4 in, and this is super important, the universe where xn plus 1 is tails, xn plus 2 is heads, xn plus 3 is heads, and xn plus 4 is heads. So where are we? We have an expression for the probability s equals n plus 4. It is 1/16th the probability s equals n plus 4 given all of these values at time n plus 1 through n plus 4. We just showed that this event is equivalent to this event, so I'm going to plug that in there instead. This is the probability s is greater than n given the rest of the stuff. And I'm going to write out the definition of this conditional probability. So I get the larger intersection on top, where I combine the things before and after the conditional line, over the joint probability of all the stuff after the conditional line. But these are the coin tosses. On the bottom, I've got 4 coin tosses. They're independent. I get heads and tails with probability 1/2 each. So again, this is the probability 1/16th, which comes from 1/2 multiplied 1/2 to the 4th power. And that is going to cancel with the 1/16th out in the front of this problem. So I am left with the numerator. And while I'm at it, let me go ahead and rewrite the left-hand side, because it's really just scrolling up away from us. And all we have left is this numerator, and I am going to rewrite this. I'm going to write this intersection using conditional probability, unraveling that definition. I'm going to write this as the probability that xn plus 1 is t, xn plus 2 is h, xn plus 3 is h, xn plus 4 is h, given that s is greater than n, times the probability that s is greater than n. So s being greater than n, that is the information that the pattern is first observed at a time greater than n. Well, these are coin flips, and the coin does not care whether or not the pattern was observed. The coin is going to give me tails, heads, 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 regardless of whether or not I observed a pattern before or after time n. So this is irrelevant. These are independent of the first pattern time. And so this is going to be, well, I'm going to drop this because these are independent. And there I have that 4-way probability again. So that is 1/16th. And I'm left with this probability that s is greater than n all the way over there on the right-hand side. So here we are. We're at the aha moment. I am going to take both sides of this, and I am going to sum as n goes from 0 to infinity, the probability that s equals n plus 4 I'm going to take out the 1/16 on the right-hand side. The probability that S is greater than N. Now on the left side, this sum is, if you look at the terms, we've got the probability that S equals 4, S equals 5, S equals 6, on up. Those are the possible values for S. This whole thing sums to 1. And then this sum over here, if you recall from a couple of lectures ago, we talked about a clever way to compute expectations using summing tail probabilities. This is, in fact, the expected value of S. So I will maybe link back if there's nothing here, and then I couldn't figure out how to do it. I'll put something else there. But we've got the 1/16 expected value of S equals 1. And this implies that the expected value of S is 16. And that's what we were trying to figure out all along. Wasn't that cool? That was cool. Because if you redo this with your own problem, that's way too small for anyone to read, I can really easily put, a pattern, a very long pattern of flips. That 1/16 could easily turn into a 1/2 to a higher power. And so we can solve a lot of problems without having to do all that work again, because we know where it's headed and we could sort of shortcut to the answer. Mean pattern times are awesome. If you have an overlapping pattern, you could do it the long way using a first step analysis, or you could use a martingale, which we'll get back to much later on. So that's it for today. I will see you next time on Markov processes.